So let us consider a vector A along the Cartesian orthogonal axis 1, 2 and 3. Here I1, I2 and I3 are the unit vectors corresponding to the axis 1, 2 and 3. So we can express the vector A into its component form as A vector is equal to I1 vector A1 plus I2 vector A2 plus I3 vector A3. Suppose if we rotate the axis by keeping the origin fixed, this leads to a new set of axes 1 prime, 2 prime and 3 prime, and I1 prime, I2 prime and I3 prime are the unit vectors in the rotated axis. Here the vector A remains unchanged, thus can be expressed in its components as A vector is equal to I1 prime vector A1 prime plus I2 prime vector A2 prime plus I3 prime vector A3 prime. Since the magnitude and direction of the vector A is not changed after transformation of the coordinate, we can express this right hand side of these two as I1 prime vector A1 prime plus I2 prime vector A2 prime plus I3 prime vector A3 prime is equal to I1 vector A1 plus I2 vector A2 plus I3 vector A3. Now, if we take the scalar product with I1 prime on both sides on this expression, so we get A1 prime as I1 prime dot I1 A1 plus I1 prime dot I2 A2 plus I1 prime dot I3 A3. So similarly, if we take the scalar product of I2 prime, we get A2 prime as A21 A1 plus A22 A2 plus A23 A3, and if we take the scalar product of I3 prime, we have A3 prime is equal to A31 A1 plus A32 A2 plus A33 A3. Here the dot products I1 prime I1 or I2 prime I2 etc. are abbreviated as A subscript LM, which is nothing but the cosine of the angle between the old M axis and the new L axis. The set of these equations can be expressed in this notation as AI prime is equal to summation j is equal to 1 to 3 Aij capital A subscript j with I taking the values 1, 2 and 3. So this expression can be considered as a new definition for vector. That is, a vector is characterized by a set of three quantities ai is equal to ai with I is equal to 1, 2, 3, which under rotation transform according to this equation. So thus we see that vector is invariant and it does not depend on the coordinate system. However, the components of these vectors are not invariant and they depend on the coordinate system. So if we generalize this statement, we can state that tensor is an object that is invariant under a change of coordinates and has components that change in a special and predictable way under a change of coordinates. So the new definition of vector that we have seen has the advantage that it can be generalized easily as follows. Suppose we have a set of 9 quantities b subscript ij with I is equal to 1, 2, 3 and j is equal to 1, 2, 3 form a tensor of rank 2 if under a rotation of axis the components transforms as given by this expression. That is, bij prime is equal to sum L is equal to 1, 2, 3 and sum M is equal to 1, 2, 3 AIL AJM B subscript LM. So this transformation accounts for a tensor of rank 2. So similarly, a tensor of rank 3 is a set of 27 quantities Cijk transforming under rotation as given by this expression, that is Cijk prime is equal to sum L is equal to 1 to 3, sum m is equal to 1 to 3, sum n is equal to 1 to 3, AIL, ALM, AKN, CLMN. So if the transformation law is right, the number of indices indicates the rank of the tensor. For example, if the transformation is right, the number of indices is 3, hence the rank of this tensor is 3. Here the number of indices is 2, hence the rank of this tensor is 2. Hence a vector which we have defined and discussed earlier is a tensor of rank 1. So matrix is a tensor of rank 2, and quantities which remain invariant under rotation are called scalars, and hence a scalar is a tensor of rank 0. So a scalar is a tensor of rank 0. So any number, the magnitude, length of a vector, temperature, constant, etc. are some of the examples for tensor of rank 0. So a vector is a tensor of rank 1, subject to the condition that it should obey the transformation law just we have discussed for rank 1 tensor. So some of the examples are velocity, displacement, etc., whose components can be expressed in a column vector notation. Stress, strain, metric tensor, that we may discuss it later, are examples for tensor of rank 2 that can be expressed in a matrix form. So a point to remember here is that a tensor of rank 2 can be written as a square matrix of order n. However, the converse is not true. That is, the elements of an arbitrary square matrix do not form the components of a second rank tensor. So here in this table we can see various order of tensor starting with scalar. So this is 0th order tensor, has no components, and vector, it is a first order tensor and it has 3 components. Dyad, it is a second order tensor. So this is a product of 2 vectors and it has 9 components. Dyadic is a second order tensor and it has 9 components. And we have triadic, a third order tensor having 27 components, and tetradic, a fourth order tensor having 81 components. So there is a relation between the rank of a tensor and its components. So we know that the rank of a tensor is determined by the number of suffixes or indices attached to it. And as a matter of fact, the rank of a tensor, when raised as a power to the number of dimensions, yields the total number of the components of the tensors and hence the number of components that represent the tensor. For example, suppose consider a tensor of rank 1 in two-dimensional space. So it has 2 power 1 components. So 2 is the space dimension and the superscript is the rank. So a tensor of rank 1 in 3-dimensional space has 3 power 1 component. So rank 1 is a vector. So if it is in a 2-dimensional plane, it will have 2 components, and if it were in a 3-dimensional coordinate system, it will have 3 components. So we can generalize this into other higher order tensors and higher dimensional space. For example, a tensor of rank 2 in 3-dimensional space has 3 power 2 components, that is 9 components. In general, a tensor of rank n in 4-dimensional space has 4 power n components, and so on and so forth. So now let us define contravariant vector or contravariant tensors and their associated transformation laws. Now let us consider a vector A in a 2-dimensional Cartesian coordinate system with the basis vectors I and j. Let A be a velocity vector and the unit of this axis is considered in feet and the unit of this axis is considered in seconds. So the vector A can be expressed in its component form as A vector is equal to 2i plus 2j. Now let us make a transformation of this coordinate by changing the scale. That is, the scale of the coordinate system is changed. So here, instead of taking feet, if we take the unit as inches, we have A vector expressed as 2i prime plus 24 j prime. So I prime and j prime are the basis vector for this transformed coordinate system, satisfying this relation. That is, I prime will be equal to I and j prime will be 1/12 of j. Or we can express the other way, I is equal to I prime or j is equal to 12 times j prime. That is, if you reduce the basis vector, what happens is there is increase in the value of the component, and vice versa is also true. If you increase the basis vector, the component will decrease. That means if the unit vector or basis vector is reduced in the primed coordinate system, which would result in the increase in the value of the components. Otherwise, if the unit vector or basis vector is increased in the primed coordinate system, that would result in the decrease in the value of the components. That is, the components changed in a way contrary to the unit vectors. That is, if it is decreasing, this gets increased, or if it is increasing, this gets decreased. So thus, velocities are considered as contravariant vectors. Displacement, acceleration are also example for contravariant vectors. So as we defined contravariant vector considering a velocity vector, we can define covariant vector or covariant tensor by considering gradient of some scalar field. For example, a gradient is change in the value of a quantity with a change in a given variable. So now let us consider a gradient of a scalar field f as given here. So del f is equal to dou f by dou x I plus dou f by dou y j. Suppose if we have the coordinate system with I as the unit vector, the behavior of dou f by dou x will be as shown here. If we change the coordinate system by scaling the axis as discussed before, either by increasing I prime is equal to 2i or I prime is equal to I by 2, either way the magnitude will behave in a way the basis vector changes. That is, if we increase the basis vector, the magnitude will also increase. If you decrease the basis vector, magnitude will also decrease. So thus we can say that if the unit vector or basis vector is reduced in the primed coordinate system, that would result in a decrease in the value of the components. So here the basis vector is decreasing and the component value also get decreases. So here the component is dou f by dou x. If the unit vector or the basis vector is increased in the primed coordinate system, that would result in increase in the value of the components. So components are changed in the same way to the unit vectors, and hence such vectors are defined as covariant vectors or covectors. So we can generalize our previous definition for contravariant vector or contravariant tensor as below. Suppose let a physical quantity be characterized by n functions a superscript I in x superscript I coordinate system. Suppose if the same physical quantity is characterized by n functions in x bar alpha coordinate system, then the components are A bar alpha. Then AI are said to be the components of a contravariant vector if they satisfy this transformation expression. That is, A bar alpha is equal to dou x bar alpha divided by dou xj aj, and the inverse transformation, that is AI is equal to dou xi by dou x bar alpha A bar alpha. So if these expressions are satisfied, then we can state either AI or A bar alpha as the contravariant vectors. So this can be understood by considering this example. Let the physical quantity be velocity in xi coordinate systems. That is, AI is given as v of x. So v having the coordinates x1, x2, x3 up to xn. So these are not powers, they are just superscripts. Hence the vector v can be expressed as dou x1 by dou t, dou x2 by dou t, and so on up to dou xn by dou t, or it can be expressed in a simple notation as v superscript I, where v being the contravariant vector, the index is used as a superscript, which is equal to dou xi divided by dou t. Suppose if you express the same physical quantity in the barred coordinate system, we have v vector is equal to dou x bar 1 by dou t, dou x bar 2 by dou t, and so on up to dou x bar n by dou t. And hence in the barred coordinate system, we can express v bar superscript I, the contravariant vector in the barred system, as dou x bar alpha by dou t. So we can expand this by using chain rule as shown here. So v bar I is equal to dou x bar alpha by dou t, which is equal to dou x bar alpha by dou x1 by dou t, plus dou x bar alpha by dou x2 by dt, plus dou x bar alpha by dou xn by dt. Or we can simplify this and express it as v bar I is equal to dou x bar alpha divided by dou xj by dou t. Here dou xj by dou t is nothing but vi, and hence we can express v bar I is equal to dou x bar alpha by dou xj vj. So this should be compared with this transformation equation. So similar to the contravariant vector definition just we have discussed, for covariant vector or covariant tensor, we have these two transformation laws as given here. Here the index is at the subscript. The A bar alpha is equal to dou xj by dou x bar alpha A subscript j, and if you invert this expression, we get ai with I as a subscript is equal to dou x bar alpha by dou xj A bar alpha. So now we shall see a problem. Show that velocity is a contravariant vector. So from our previous discussion, already we know that the derivative of xi is given as dxi is equal to dou xi by dou x bar alpha dx bar alpha. So if you divide this by dt, so we have dxi by dt is equal to dou xi by dou x bar alpha dx bar alpha by dt. So if you denote dxi by dt as vi and dx bar alpha by dt as v bar alpha, we have this expression indicating that velocity is behaving like a contravariant vector. So similar to dxi, if you take the derivative of the barred coordinates dx bar alpha, which is equal to dou x bar alpha by dou xi dxi, we may get an expression satisfying this transformation law, for the velocities. That is v bar alpha is equal to dou x bar alpha by dou xi vi. Thus, velocity is a contravariant vector. So far we have discussed about the transformation laws or the transformation expressions for covariant and contravariant vectors, that is tensors of rank 1. Now let us consider uh, tensors of rank 2 and their associated transformation expressions for contravariant and covariant and mixed transformation. For contravariant transformation, let us consider a set of n square functions a superscript ij in xi coordinate system, which are said to be the components of a contravariant tensor of rank 2 if they transform according to this expression. So a bar alpha beta is equal to dou x bar alpha by dou xi, dou x bar beta by dou xj, a superscript ij. So similar to this transformation law, we can define the same for a covariant tensor of rank 2. So a set of n square functions a subscript ij in xi coordinate system are said to be the components of a covariant tensor of rank 2 if they transform according to a bar alpha beta, where alpha beta is in the subscript, is equal to dou xi divided by dou x bar alpha, dou xj divided by dou x bar beta aij. So having defined the transformation laws for contravariant tensor and covariant tensor of rank 2, let us see the transformation expression for a mixed tensor of rank 2. Let consider a set of n square functions a superscript I subscript j in x superscript I coordinate system, which are said to be the components of a tensor of contravariant rank 1 and covariant rank 1, or simply a mixed tensor of rank 2 if they transform according to the expression given here. That is, a bar superscript alpha subscript beta is equal to dou x bar alpha divided by dou xi, dou xj divided by dou x bar beta a superscript I subscript j. So this is transformation law corresponding to a mixed tensor of rank 2. So we have already discussed some of the properties of Kronecker delta. Now let us see that Kronecker delta transforms like a mixed tensor of rank 2. So let us consider the Kronecker delta in the barred coordinate system, that is delta bar superscript alpha subscript beta. So we already know delta bar superscript alpha subscript beta can be expressed as dx bar alpha divided by dx bar beta, which is equal to dou x bar alpha divided by dou xi by dou x bar beta. So this term dou x superscript I divided by dou x bar beta can be replaced as dou x superscript j divided by dou x bar beta delta ij, because since delta ij can take only either of the value of 1 or 0, we can have I is equal to j, that would lead to dou xi by dou x bar beta. So this transformation confirms that the Kronecker delta behaves like a mixed tensor of rank 2, and since the only value delta can take are 1 and 0. Further, this Kronecker delta has the property that its components are same in both the coordinates, that is delta bar I j is equal to delta ij, and hence Kronecker delta is called as isotropic tensor.